You can hear me? Cool. So I'm Saam. I'm a director of language engineering at Epic Games. I manage a team of people working on creating a VM for the verse language. So today I'll give a quick overview of the verse programming language, and then I'm going to talk about two projects my team has been working on for 2 years and 2.5 years for the other one. New bespoke VM for verse, so we're creating entirely new VM for running verse, and we're also creating AutoRTFM, which is a project for bringing software transactional memory to C++ code, so it's both a compiler and runtime. I encourage you to interrupt me in the middle of this talk. Don't wait till the end to ask me questions. So let's talk about verse. So verse actually is a programming language created by Tim Sweeney. Tim Sweeney's the founder and CEO of Epic Games. And when you hear Tim talk about verse, he created verse as sort of a programming language for what he describes as the metaverse. And when you hear him talk about that, he'll sort of describe it as a programming language for a shared open world 3D simulation. The way I like to conceptualize the programming model for verse is as if it's running on one massive computer with one shared heap. So everybody's code is running on the same heap, and code is running sequentially on a single thread. This is, of course, as if how it's running. This is not actually a scalable way of implementing verse. And the unit of execution on this massive computer is a transaction. Today, we have shipped verse to the public. It's a much smaller subset of the fully realized language we want. But today we have Unreal Editor for Fortnite. This is a tool that non-Epic developers can use to create islands on Fortnite. So when you go and play Fortnite, you can play Epic created games like Battle Royale. You can also play games not created by us. And those games are programmed in verse. So verse is multi-paradigm, so it's strongly typed. There's actually a lot of really interesting aspects to verse's type system. Sorry, I'm not going to be talking at all about verse's type system, but if you want to talk to me about that afterwards or talk to these gentlemen about that afterwards, please do. Verse has a really powerful functional subset to the language. It also has an effect system that lets you guarantee that you're running within that functional subset. There are aspects of logic programming to verse. It has unification variables. There's what we call lenient execution in verse, which is programs can run out of order. So unlike lazy evaluation, all of your program runs, but the order in which it runs is sort of determined dynamically based on values being available to the runtime. And there's object-oriented programming in verse, so there's classes, there's interfaces, there's inheritance, nominal subtyping. There's also a really powerful imperative subset, so you have pointers, you can read from those pointers, write to those pointers, and you also have transactions. So the unit of execution in verse is a transaction. Leniency and transactions are where I'm going to focus the main two parts of my talk today. So let's go through learning verse quickly. I'm going to skip over a lot of details, but this will give you an idea of sort of what the language looks like. So here we have variable x. It's immutable. It's unified with the value of 42. And when we print it, we print 42. That's pretty simple. You also have arrays in verse. Here we're defining an array with two elements, 42 and 666. And you can access the array using this subscript notation. So when you print the first element in the array, you print 42. When you print the second element, you print 666. This is pretty straightforward. Of course, you have expressions. So here we're unifying the variable y with 2 times x, and then you get the expected value when you print y. And of course, you can have functions. So here we're defining a function f. Takes a single parameter x, which is of type int, and then function f also returns int. So it takes x as input, multiplies x by 2, returns that value. So then you can define y. and unify it with the value f applied to 42, and similar to this, prints 84 as well. You can have classes inverse. So here we have a class named foo. It has two fields. The first field is a, which has a type int, and it has a default value of 42. And then you have a second field, f, which is a function. That function takes one input, returns also an int as output, and it adds the field a to the function parameter b. On the next line, we're defining x to be a foo. So we have x, which is an instance of foo, and the right-hand side of that unification is what we call archetype instantiation inverse. So the braces form an archetype. That archetype provides a value for a. Then we invoke the f function field on foo, passing it 1, so we add 1 to 666.
Can you also change the add?
Yeah, you can. Yeah, so that sort of traditionally is on a per instance, you can overwrite methods. Yeah. So verse has a really nice for loop semantics. So for loop inverse is really map. So here we have that same X array from a previous slide. We're iterating over every element of X, binding it to the variable E, and the body of the for loop actually produces the result E plus 1, and the entire for loop expression produces sort of this mapping of element in X to element in X plus 1. So you see that the array produced by Y is the same as the array produced by X, except every element has 1 added to it. Verse also has stackful coroutines. So here there's a primitive in verse called spawn that lets you spawn a coroutine that's not parented to any other coroutine. There's other primitives related to coroutines that I'm not going to go into. This my coroutine function, it defines a variable X, and then it calls into an API function called sleep. Here, when you call sleep with 0, actually what the game engine's doing is it's going to run this function again. It will resume this function after the next frame of the game engine begins. So yeah, stackful coroutines, they exist in verse. And you have mutability. So here we're defining a var x of type int. So really the way to read this is x is a pointer. We allocate a box for the value 42. We can read from that pointer. So we print 42, we can mutate, so we can write to that pointer, setting x to 666, and then we can print it again. Verse also has what we call live variables. Similar to reactive programming, it allows you to program a little more declaratively. So here we have a variable x, but we have a live variable y, which we bind to sort of the expression x plus 1. And what happens here is anytime x changes, we reevaluate this expression and store it into y. So y starts off as 42 plus 1, but then as we change x to 666, y reevaluates x plus 1 and stores 667 into y. Yeah?
If the body of y had been, for instance, to add x to a random number, then would that random number, if the body of y had been to add x to a random number, so that random number effect has to occur at some point.
Yeah.
Does that occur every time y is accessed or every time x changes?
I think it depends on how you model your random number generator. So in verse, you would probably model calling a random number generator as like it has some value that it mutates on every new call to that random number generator. So in verse's effect system, you would say that random number function both reads and writes. And actually, the right-hand side of a live variable expression can't have a writes inside of it. It can only have a reads expression.
Okay, so you wouldn't be able to do a side effect in that case?
Yeah, exactly.
Great, thank you.
Yeah. So verse has failure. So control flow is done via this construct called failure. So in C++, if you see like x greater than 200, that's an expression, it returns a Boolean. In verse, we say that expression can succeed or fail. So if x is greater than 200, it succeeds, and if it's less than or equal to 200, it fails. And you embed failure within what we call a failure context. So here, the if statement takes an expression for its condition. That condition may succeed or it may fail. If it succeeds, you run the then, and if it fails, you run the else. So here, we're testing if 42 is greater than 200, which it isn't, so we print, we run the code at the else, printing less than or equal to 200. And unification also might succeed or fail. So similarly to the previous example, we're trying to unify x with the value 200, that fails. You can abstract over failure. So here you see f is declared with the decides effect, saying f may succeed or it may fail. So this is exactly the same as the previous example, except the function f is doing the thing where it's testing if I is greater than 200. Failure contexts show up in a lot of places in verse, but one of the most interesting places is in the for loop. So for loop, what we call the domain, so like the condition of the for loop, is a failure context. So here, the range, which is the body of the for loop, only produces values for items in the range that succeed. So what we end up doing, like the previous for loop, is we iterate over every value of x, but we only run the body for the elements e, where e is greater than 6. So we end up producing just the slice of the array here, where the element is greater than 6. So for loops in verse are sort of both map and filter built into the same construct. Next, we have sort of the intersection of failure contexts and transactions. So again, the unit of work in verse is a transaction. So when verse is running, it's always running in a top level transaction. And if you remember the coroutine slide, we have these functions that are suspends, and a transaction in verse is running between two suspends points. But you can also have a nested transaction in verse, and every failure context creates a nested transaction. So what's happening here is we have this var x, which starts off as 42, and in the failure context, we first set x to 666, but then we test for y less than 0. That fails. And what that ends up doing is failure in a failure context is also aborting the transaction of that failure context. Does this example make sense to people? Yeah, exactly. Yeah, so this is creating a nested transaction. The effect in this nested transaction is just one thing. It's writing the value 666 to the pointer x, which is a pointer to an int. And that store to memory has to be undone if the transaction's aborted.
So if I'm not putting this y smaller than 0 in this if branch, it's just like putting in a no more like sequential statements. Does that like negate the entire?
So a top level transaction is running in a context that's not decides. So a decides context has to be embedded within a failure context, but we are always running in a transaction. So the way to abort the top level transaction is actually via a runtime error. So you can still abort it, but the program y less than 0 at the top level wouldn't type check.
But if you put it in a function, then that is annotated decides. If it fails, the whole function is aborted.
Yeah, like this. So like here, if you also had effects inside of f, if I were less than or equal to 200, those effects would be undone. And that nested transaction, so this is the version of the nested transaction that fails, therefore aborting the transaction. But you can also have a version of that transaction that succeeds. And when the transaction succeeds, that transaction is committed. So here, the inner transaction that sets X to be to 666 commits. And then when you print after that transaction, X is still 666. And I think kind of getting at what Jan was talking about, like that one write to X isn't the only effect that's possible, right? Here you can have any arbitrary effect happen, and if Y is greater than or equal to 0, it should be as if that effect never happened. Does that make sense? Yeah.
Does it propagate to the function that is not pure? Like, say, does it propagate to the function that is not pure, saying that I'm printing something, right? Or like sending a packet?
Right.
Or are you going to commit the effect after?
Yeah, so like some effect here might be like send an RPC from one process to another. Yeah, so that's actually like really interesting implementation detail. So we usually have code, like the code we've written along those lines have often been like, send this RPC packet once the transaction commits. And in that case, it's the top level transaction, because you can have, this transaction can be nested somewhere way deeper in the transaction stack. What you care about is if my root transaction commits, then send the RPC request, or then store the file to disk. I think there's.
So you keep saying on one hand that, oh, and if the transaction aborts, then we undo it. And you also say if it succeeds, then we commit it. But like, how should I put it? Like only one of these makes sense, right? Because either you say that things don't really happen until they get committed, or things happen instantly, but they might be undone. So which one is the model here?
I guess I don't.
Yes, but is there something happen, like is
Right, so when you're in this transaction, so I don't know if I have a pointer. If you're running code here, that sees X as the value 666. So while you're running in the transaction, the heap is as you've been mutating it in the middle of that transaction. So committing it is not a lot of work, right? Like you've already performed the mutations you wanted to. So code within the transaction sees as if the transaction will commit. It's just if failure is encountered, it's as if no effect in that transaction happened at all.
So maybe what I want to ask is rolling back expansive or is committing expansive?
Rolling back.
Okay.
The way we've implemented it.
Okay.
Yeah.
That could have been implemented the other way, right? I mean, it's just an implementation choice
Yes.
at that point, right?
Yeah. It is an implementation choice in terms of the performance cost, but the semantics are not an implementation choice. The semantics inverse are well understood. Yeah.
Suppose I had two effects back to back, one of which was sending a message and one of which was receiving it.
Yeah.
And after both of those occur, then I have a choice that might possibly fail.
Yeah.
It seems like it would be very hard. So for instance, if the message I receive is a function of the message I send, and there must be some real world other server that has to have actually gotten that message, how can you reverse that?
So the only way to see the passage of time inverse is via suspends context. So to see the passage of time, you have to have executed a suspends function and then resumed from it. So if we created APIs for like send network packet, receive network packet, those would both likely be suspends calls. So they would be one like you can't, we don't allow you to write that suspends call in the middle of a transaction, in the middle of a failure context. They can still be in the middle of a transaction because verse is always running transactionally, but the only way to abort that transaction is via a runtime error.
So you can't act on the outside world and see the result within the same transaction.
Yeah, exactly.
It is a domain-specific language for gaming, right?
Yeah.
Yeah, but like launch the nukes would be a suspends function in verse.
And so mutation in this case is a special case where it's
Well,
something that
mutation
is...
seeing the passage of time, right? So the way to think about verse is that like a transaction, here's how I think about it. Transaction executes instantaneously, and sequential transactions are where the observation of time can happen.
But I can observe within the same transaction a mutation that has happened in this transaction.
Absolutely, yeah.
So doesn't that kind of violate that reasoning where it
So
seems like I would have to wait until...
So sending a packet, what you can view that as is code that runs telling you to commit the transaction you're in, then you send the packet in its own isolated transaction, then you run the code after sending the packet in the subsequent transaction after that.
Okay,
That's how I reason about it.
okay.
This is good stuff. So
I'm not sure what you call the thing inside the if condition, but
yeah,
let's call
a
that.
failure context.
Okay, so in a failure context, you can be kind of monadic over function calls that only have effects that can be rolled back, but you can't be monadic over functions that, or anything that has effects that you can't roll back. Is that what's basically going on?
Yeah, sure. That's one way to think about it. Yeah, like you can't launch the nukes in a failure context.
Yep, okay. Yeah, sure.
All right. Talked about that. So next is leniency inverse. So this is what I was talking about earlier, where programs can run out of order. So here we have a unification variable x. It's of type int. It doesn't yet have a value. We print x, and then we unify x with 42. This does what you would expect it to do. It would run the same way as if you moved that unification above the print. Similar to our previous example, you can not just print unbound unification variable, you can have expressions that run across unbound unification variables. So here, y is unified to 2 times x before x has a value, and we print y before y has a value. And this prints what you would expect it to print. And you can abstract over leniency. So here we have a unification variable, we pass it into f, we multiply it by 2 before x or I, when viewed in the f context, has a value. Does this make sense? This is one of the more tricky things in verse, yeah.
What does the closed mean?
Yeah, let's ignore the close for now. Talk to me later, yeah. It'll show up in a couple more slides. Let's ignore it for now. I have a slide about that in 1 second. The programs, effects run in program order. So here, also you can have a function that takes in a unification variable and unifies it within the function. So here, kind of ignore both calling f with square brackets and the closed. We can talk about that elsewhere. It's sort of not the interesting thing here. And these values in verse are really unification variables. So here we have 3 unification variables, x, y, and z. We unify x with y, y with z. So after that point, x, y, and z are all equivalent to each other. And just by unifying z, it's as if, because there's an equivalency, all variables gain values. Does this also make sense to people? Cool. Here, similar to this example, of course, you can abstract over this. So similar to what you're asking, what happens with leniency and effects? So here we have a program. The effects in this program are writing to x on line 3 and line 4, reading from x on line 5, writing to x on line 6, reading from x on line 7. These effects have to happen in program order. That's the semantics of verse. But Notice that the then and the else of the if statement both are effectful. And we don't know if we should take the then or the else until y has a value. So here, we run this entire program before unifying y with the value 201. And only after we unify y can we then determine that we should be running the then statement. So what happens in verse is it's as if that y equals 201 were hoisted to line 2. That's the way to think about how this program executes. So once you unify y with 201, that allows the failure context to determine it succeeds. That runs the then on line 3. That running that then allows the read on line 5 to execute. Running that read allows the write on line 6 to execute. Running the write on line 6 allows the read on line 7 to execute.
It'd be a correct way of modeling in my head that when you get, like you start from the top, and when you get to a branching on y greater than 200, it's blocked on not having a value yet for y. So you like queue it somewhere, the continuation, which is both branches at this point, because you don't know which one to get. And then you keep going, and it gets unblocked when you know that the unification of y could potentially give it a value, and now it is a value, so then it unblocks this. Is that a good model of thinking?
Yeah, and that's actually a little bit how we implement it. So I'm going to talk about how we implement leniency in the new VM in the next section. You have a few people.
Oh, how it runs when y is dependent on x?
So depending on how you wrote that program, that would be stuck. The verifier would say you can't, there's nothing it can do to unblock this program, so it would be rejected by the checker.
Possibly a very obvious one, but I assume if you didn't set x in one of those branches, it would still have to wait. Like the possibility that x might get set means that you have to wait on all those.
Yeah, because you don't know if you're running the then or the else until y gains a value.
When do the reads of x happen on those prints? Does it happen before you call the function?
Yeah.
Okay.
One more time.
Sorry, I know this is probably going rather long.
It's okay. Well, I'll skip around a little bit later to make sure we finish.
So suppose I have so you mentioned that there's a verifier that makes sure that a variable is assigned. Is that it seems like that verifier need necessarily be conservative, right? In the same way that I might have, if this Turing machine halts, then assign a value and then print that value, right? That only, the verifier would then need to solve the halting problem in order to correct that problem accuracy. So is it conservative? Is it overly liberal in that it will sometimes allow those kind of stuck states to occur?
The verifier will never, so this verifier isn't finished yet, but the goal of the verifier is to never allow a program that's stuck to check.
Okay, that makes sense.
All right, let's talk about the new VM. So I told you at the beginning, you can publish verse programs today. So we have an existing VM. The existing VM is built on top of Blueprint VM, which is a VM designed by Epic for the Blueprint scripting language. It's a visual scripting language. It's not designed for verse. The part of the language implemented in what we call the old VM is ship verse, which is really reduced subset of verse. Doesn't have unification variables, doesn't have leniency, doesn't have lambdas, doesn't have live variables, doesn't have a lot of things that we want to build into the language. So there's just this huge impedance mismatch as we implement things in the old VM. It makes it really difficult to implement new language features. This is not a VM designed for verse. It's also really inefficient. One example of that inefficiency is like any object in the system is like 400-ish bytes or something like that. So our new VM designed for what we call MaxVerse. MaxVerse is the fully realized version of the language that Tim wants. It has leniency built into the semantics of how we execute bytecode. Smallest object size is 16 bytes. We still support compatibility with UObjects. That's how folks writing sort of FFI APIs to Verse, they use UObjects. We can still support them. We have what we call Franken GC. So Unreal Engine has an incremental stop the world garbage collector. For UObject space, we, for our vcell space, have concurrent mark and sweep, so we can mark concurrently and sweep concurrently while the mutator is running, but the UObject space can only mark with the world stopped. And one of the guiding principles for the VM is static in the front, so Verse is strongly typed, but Verse is also highly dynamic. So the VM is itself dynamic. For example, there's only one add bytecode in the VM. It both is responsible for adding ints, adding floats, adding two arrays together, stuff like that. The bytecode format is a linear instruction stream, register-based, untyped. The unit of value is what we call v-value. These are 64-bit NAND box values. Control flow is done primarily through failure. And unification and leniency are like built into the interpreter and bytecode semantics from the ground up. We can skip this. V-values are 64-bit NAND box values. This is what a bytecode instruction looks like. Here you have the add instruction. Takes two inputs. The left side is R1. R1 is just a pointer into the frame. R2, the right-hand side is also a pointer into the frame. We unify that result with R3. We'll get into unification in a second. That's what a bytecode instruction looks like. Here's a really simple example of one of these programs running. So here we have the bytecode for F. F takes two parameters, multiplies them, returns them. So we see that when we're running F, if we called it with 42 and 2, we can see R1 and R2. Those are the two arguments to our function. I'll have the value 42 and 2. We see we run this R3 arrow reset instruction. What this is doing is creating a fresh unification variable. We'll get into that a little bit more in a second. We then multiply R1 with R2, unify it with R3, and then return that from the function. This is pretty basic bytecode interpreter, register-based bytecode interpreter stuff. All right. So now let's look at how we do leniency. So here we have this function f. Similar to our previous example, takes one parameter as input, but you'll see that we multiply x and y together before we have a value for y. So here, R2 is y and R3 is z. So we create unification variables for R2 and R3. And then the interesting bit happens here. So we don't actually have a bound value for R2 or R3. But what we want to do is run the instruction mul R1, R2. Sorry, we don't have a bound value for R2. R1 is a bound value. It's the parameter to this function. But we don't have a value for R2. So we can't actually run this multiplication yet. So I'm going to talk about how we do that. So the main idea, I think similar to what you were getting with your mental model, is how do we execute these lenient semantics? So the VM is designed really with this idea that computation can be captured into what we sort of call like a suspension closure, which closes over all of the inputs necessary to perform the computation. So in the case of mul, it will capture dynamically when it encounters leniency, both of its inputs and its output, into a closure. And then when its inputs are resolved values, it will run that closure and unify with its output. So unification variables in the VM have 3 states. All unification variables are created as what we call a root unification variable. So when you run the reset operation, we're creating a root unification variable. And then there are 2 primary transitions that happen. So you can transition from root to value. So this happens when you, let's say, unify x with the value 42. But something really interesting happens there. So when you're a root, you have a list of suspensions that have to run once you gain a concrete value. So when you transition from root to value, you take this list of closures and then you execute them. You can also transition from root to pointing to a parent unification variable. That happens when you unify 2 unbound unification variables. And what happens there is you pick one to point at the other, but you join their suspension list together. And these unification semantics are built into the bytecode. So what we have, when you see equals in our bytecode textual format, what that means really is you're unifying with the result of the operation. So it's not just a def, it's both a use and a def. And then we also have what we call a clobber def. That's that arrow, and reset is actually the only operation today in our bytecode that has these semantics. And that writes directly into the frame. And reset is the only operation that does this, and all it's doing is creating you a fresh unification variable. So if we go back to our example, look at it a little bit more detail, we see that we have 2 placeholders. We have a placeholder for R3, which is just a unification variable for R3, and we also have one for R2. Let's call those P2 and P3. They're both starting off as these root unification variables, and they both have an empty suspension list. So when we go to run this mul, we see that R2 doesn't have a value. And what we do is we create this closure called a mul suspension that captures the left-hand side, that's the value 666. It captures the right-hand side, which is P2, the placeholder or unification variable for R2. And it also captures P3, the output of this operation. And then it also enqueues itself on P2's suspension list. So when P2 is unified with a concrete value, we run this mul suspension. And then the next instruction will unify P2 with that concrete value. So it unifies P2 with 42, so you can sort of see that designated.
But shouldn't S also be blocking on P3? Because, you know, if I know that X times Y is 84, and X is a parameter and it's 2, then Y can be solved by unification as well. You can go either way.
Yeah, sure.
So in this...
Well, yeah.
Does that work?
So that, like, sort of prologue style evaluation isn't built into verse directly. Like, you have to write code sort of manually to get the, like, backwards aspect of that.
Oh, so there is directionality here.
A little bit, yeah. But it is true that you can also have another line of code which says Z equals, or Z unifies with 84, and that must hold, but it won't solve for Y.
Yeah, that's what I meant. So there is directionality.
So it won't solve.
Yeah,
It
okay,
won't solve for
okay,
Y.
okay.
Yeah.
Suppose that you had 2 suspensions which were mutually exclusive. So say one of them was a suspension that, oh, this is the product of two variables which are both positive numbers. And then another suspension which says that same variable is the product of a positive and a negative number, such that one of those 2 suspensions must be untrue. Is the verse VM?
Yeah, you can fail. So there's no guarantee when you either run in order or via suspension that the unification succeeds. Okay. All unification might fail. Yeah, exactly. Yeah, you have to evaluate everything. Like both of those suspensions will eventually evaluate, and one will fail based on your construction.
Okay, thanks. Do you perform occurs check on it?
A what check?
Occurs. Like,
What?
can Z use itself in what it is supposed to unify?
I think that will be stuck by the verifier.
Okay, so you can't, because sometimes you can generate structures with this.
Oh, like Z equals Z times 2?
Possibly, or Z equals Z times 1.
Sure.
Or you can
Yeah,
generate
that's- the
a
VM
lazy
will-
structure which...
Yeah, the VM will execute that faithfully.
Okay. And also, another question, does L value need to be a variable, or can it be a pattern as well, or like an expression too? Can I write x plus 1 equals 1 plus x?
I think so. Yeah, why not? Yeah, definitely. Okay. Yeah, all values are unification variables and at the VM level, but I think also you can definitely write x plus 1 equals 1 plus x.
I'd like to clarify what I think the previous question was trying to ask. So I assume this is all shallow. So if I have some tree-like structure, I can have a function that is only blocked on solving the top level of that. Like, let's say it's literally a binary tree, then I can have something that's stuck on whether the top is a leaf or a branch, sure, without knowing it. And then in this case, the occurs check question makes a ton of sense, because then can you have something like T equals a binary branch of T and T?
I'm not sure I'm following T and T.
Please stop me. Okay, so you can't even have like an infinite list, which is like...
But the interesting bit there is the VM isn't opinionated about that aspect. I think that's actually like a detail of the checker that's like, yeah. All right, so we were here. We're unifying a value with R2. That unlocks the multiply from running, which then unifies the value with R3 in the unification variable P3. We see that here. P3 now gains this 27972 value, and we can return it from the function. I think I'm going to skip this because I'm running out of time shortly, but does that make sense? If people want to see like a more interesting leniency example, feel free to come talk to me. There's interesting ways that like are beyond just one instruction. I will also skip how we optimize this. I guess I'll give you a really quick high-level overview. We don't actually allocate a unification variable for every value in the program. That would be super wasteful. So one key optimization we do is if you create a unification variable and you never unify it with another unbound unification variable, and if you unify it with a concrete value, essentially the isRoot thing where you don't have a child pointing at you, we don't heap allocate you, and when you go to unify, you just store that value directly in memory. Okay. So a turn from leniency to transactional memory. Anyone have other questions on leniency before we go to transactional memory? All right, cool. So this is our transactional memory example from earlier. Nested failure context, setting x to 666, that fails, reverts the store to x, print x, it's 42. So what happens when that set x equals 666 is actually some function written in C++ code? Right, we still want that function to undo all its effects. And this really was the motivation for creating AutoRTFM. So today in the API exposed to verse programmers, we have over 300 APIs backed by C++ code and Blueprint code. Blueprint is its own bytecode format that runs via a C++ interpreter, so we can also run that Blueprint code transactionally. And UE has more than 16 million lines of C and C++ code. I think this is CLOC of unrealengine.com/engine, so it doesn't even include all the Fortnite code. We wanted an approach to transactionalize all this C++ code that was largely automatic. Our old approach to this were extremely manual. We had two functions, basically, on commit and on abort, and then every function that was transactional and written in C++ was written using these two primitives. And I think basically every single version of this function I saw got it wrong somehow. So no one got it right writing code this way. So AutoRTFM stands for automatic rollback of transactions on failure memory. Of course it does. So what is AutoRTFM? So it's a single-threaded implementation of software transactional memory for C and C++. It's built on top of LLVM and Clang, and we have a tiny runtime to go along with it. So the main architecture of AutoRTFM is we run at the end of the LLVM optimization pipeline. We take the entire input program and we clone it to create a transactional variant of every single function. The main thing that transactional variant does is record all stores to memory. So what we're trying to do is intercept before a store happens to memory so we can record the old value of that memory location, so when a transaction is aborted, we can undo it. This is what we call the write log. We also insert traps for unsupported instructions. For example, this is the 16 million lines of C++ code, like that code will like grab a lock, for example, right? So what do you do in that case when you're trying to make it transactional? Today, we don't allow the code running under the transactional memory runtime to do that. That'll just be a crash, and the code has to be rewritten to accommodate it. So terminology, we call the uninstrumented C++ code open. We call the instrumented C++ code closed. And we have these primitives. We have transact, it takes a lambda, runs that lambda in a new nested transaction in the closed, so in instrumented code. You have the abort primitive. This aborts the transaction you're in. You have open that takes a lambda and runs that lambda uninstrumented. So sort of same old C++, you know. You have close, which also takes a lambda, runs the version of that lambda instrumented. And then you have those same two on commit and on abort callbacks. And on commit runs the input lambda when the root transaction commit, and on abort will run the lambda it's passed when the transaction or any parent transaction it's in it aborts. So I think someone was asking me about like RPCs earlier, like the way we implement RPC under this scheme is like on commit send RPC. So we're gonna, similar to learning verse by example, we'll learn AutoRTFM by example. So here, pretty simple code. We have a int x outside of a transaction mutates x, and of course we print the mutated value. But that transaction might also abort. And when it aborts, we undo the store to x, and we print the original value prior to the transaction, which was 42. This is what the code would look like to you if you were programming against the AutoRTFM API. So like you as the C++ programmer working at Epic, this is the code you see. Does this make sense?
Your transaction is really transparent.
Yeah.
You wouldn't write this.
You would write the transact part for sure, and you would write the abort part.
And the open version of this, does that just set x to 666, or does
Yeah,
it?
the open version of this sets x to 666, but if you ran abort, that would, if you're not in a transaction, that would crash because it would be like, why are you calling abort from not within a transaction?
So the open version of this crashes after setting x to 666?
Yeah.
Okay.
So you can have nested transactions. So here you have a top level transaction. That top level transaction sets x to 666. Then the nested transaction increments x. Both transactions commit, you get the expected value. But of course, your inner transaction might abort, in which case the top level transaction, the store to 666 succeeds. You then run the inner transaction, increment x to 667, abort that transaction, revert the value back to 666, and then that's what's printed after the transaction. The code in the open isn't run transactionally. So here you have a top level transaction. It stores x to 666. Then in the open, we run code that increments y by 1, and then we abort the transaction. So the store to x will be reverted by the transactional memory runtime, but the store to y wasn't instrumented by the transactional memory runtime. And therefore, y is incremented from 0 to 1, not transactionally. This, in practice, is like useful if you have logging and stuff like that, to run that code in the open, not transactionally. We have these on-commit, on-abort APIs. So here we have an API where we increment x by 1 on commit, and then we decrement x by 1 on abort. So here we have a transaction that commits, so we end up setting x to 666, then on commit, incrementing x by 1, so we end up with 667 at the end. But of course, that same transaction, we might abort it, and in that case, we first undo the stores to memory, and then we run the on abort handlers. So we undo the store, reverting x back to 42, then we run the on abort handler, decrementing x by 1, we end up with 41. So here's sort of what happens in the compiler when we go to implement that code. So the code on the left is like what you as an Epic developer sees when you're writing C++ code. The code on the right is what our compiler instruments and inserts into that closed variant of the function. You see this record write call before the store to x. And so record write takes 2 parameters. One is a pointer, one is the number of bytes that will be stored to at that pointer location. So here int is 4 bytes. And what we'll do is for the first store to x in the transaction, we'll record that in what we call our write log. And then if a transaction aborts, we undo the write log. I guess, interestingly here, y is a local variable to the transaction. It doesn't actually need to end up in the transaction log. I'm gonna skip over that mostly. So how does this work at a deeper level? So for transact, we still have the record writes here, but when transact runs, we create a landing pad for the code to land back at when an abort happens. So we actually use set jump, long jump for that. So transact will set jump, we'll allocate a transaction data structure. The inside of this lambda is similar to what we saw before. And what abort is turned into is essentially undo the write log, run the on abort handlers, then deallocate the transaction, and then jump back to where that transaction started. And if you reach that else branch, it means that the transaction was aborted. Any questions on that?
So I'm wondering what happens. I guess you can also have functions calling more functions in your lambdas, right?
Yeah, totally.
And those, if you have them instrumented with your Clang, then those would all be marked, I guess. But do you know if you're calling functions that are not compiled with your runtime?
Yeah,
like if someone just imports some other library and then links it against it and then stuff just goes horribly wrong.
Yeah, we have like decoding libraries that are implemented or included in Unreal Engine, not at source, but like on an executable level. So far, we've been able to run all of those just in the open, and it's fine. Stuff like that makes that easy. But if we had a scenario where we had to recompile it, I think we would.
Okay, so you don't have any form of tagging on those functions to have like some meta info. Okay, thank you.
I was expecting just the long jump to be in the ifc and all the ceremony to be on the side, like in the else branch.
I think you can, So I have to remind myself why it's this way, but I think it has to often do with you want your stack frame to be there if you're undoing any writes to it. This is also just like what the code does today, so I transcribed it literally to this. There might be some subtle reasons I'm not remembering why. Because when I went to read the code to make this slide, I also in my head thought it would exist on the else branch, but it doesn't. So let's look at an example real quick. So here we have two variables. They're written to by the transaction. So here we have a pointer in memory, we have a write log, and we have the actual value in memory. So when we go to run this function, before we store x to 666, this was the first time this transaction is storing x, so we record the old value in the write log. Then we actually store x into its address in memory. Then we record write x again, but x was already in the write log, so we skip writing x, the old value of x to the write log. If we did that, we would be undoing x to the wrong value when the transaction aborts. Then we increment x by 1. Same thing when we record write on y, we store the old byte to our write log. Then we actually do the store to memory. And then when we go to abort the transaction, what we do is we run through our write log and revert the values that were in the write log to memory. So in this case, we return the values to 42 and a. I will skip this example, but if you're interested in a transactional malloc and free, ask me afterwards. So how does RTFM and the new VM interact together? So the new VM is run completely uninstrumented. It handles transactional memory for verse, the verse heap not written in C++ code on its own. It has its own transactional data structures. We want the new VM to be really fast, and this approach has a cost on performance. But the two software stacks are tied very closely together. So when you have a failure context in the new VM, that actually starts an RTFM transaction. And then when the VM calls into native APIs written in C++, it transitions from open to closed along that boundary. So let me quickly give you some results. So AutoRTFM, if you go onto Fortnite today and you play a UEFN island, that's running on a server with AutoRTFM compiled executable, and it's on at runtime. So that project shipped as of a couple months ago. I think we started it maybe 2.5 or 3 years ago. And then the new VM we started almost exactly 2 years ago and is gonna begin rolling out in November, and I think we'll probably be done, if I had to guess, probably like March of next year. AutoRTFM is not free, right? So the cost we've seen, this number is coming from running a set of benchmarks on Blueprint VM. So this might in some ways be a pretty aggressive example. We're running an interpreter through AutoRTFM. What we've observed is about like a 3.5x slowdown in that case. And what results have we seen for the new VM? So the new VM is already like 5.25x faster. This was taken 2 months ago, so I don't know where we are today. But this is sort of ballpark how much faster we are. And we've spent very little time optimizing the new VM already. We've obviously thought deeply about its architecture and making it efficient, but like this is just the beginning, right? We just have an interpreter. We don't have a baseline JIT. We don't have an optimizing JIT. We do no speculative optimization. And looking at, so this is result on what we call vBench. vBench is just like a benchmarking suite we created. It's not as extensive as we want it to be yet, but it's a kind of a good BS check of how fast we're performing. If you break that down into individual benchmarks, this is how we're doing on those. We're faster across the board. And I think we can get a lot faster. For context, we're, I think, probably like 10x slower than a JavaScript interpreter for a similar program. So even though we're much faster than what we used to be, we're still pretty slow. I'll skip that, and leave it some time for any more questions.
I guess one of the things mentioned in the beginning is that you're looking for soft real-time guarantees. I guess how does there's some tricky stuff going on with the VM that feels like it could potentially be a counter to that. So I'm wondering how well are you finding it fits the soft real-time guarantees, and what sort of engineering decisions are potentially related to that?
I think the main decision we made to meet that guarantee was just having concurrent GC. I think largely we're relying on developers writing their games to be fun, and to be fun, you don't want your game hitching. So we're largely relying on them putting in the work to meet like the fun criteria for a game. We're not doing much else besides that. Obviously, lots of choices in Unreal Engine are within this constraint, so we're just living with those choices.
So in the previous example, you mentioned that you can put open in a transaction. So do you see people using that in a creative way to, like, say, this is a new programming model, right? Yeah. So if you put some open, then people can bring themselves back to the comfort.
So the interesting thing, this project has taken, 2.5 years. The hardest part is actually that one bullet point on the first slide, which was all of the illegal instructions are code we've had to go and change and make work within the system, but still we find ourselves where like 99% of the system is transactionalized automatically. When we first began our conversion, so like that 2 years, we often were moving code into the open, and we found that actually, with our approach, leads to lots of bugs, usually memory corruption bugs. Let me give you an easy example. If you have an array and you mutate that array both in the open and the close, you're gonna have memory corruption. So our current approach is to put as few things in the open as possible. But if you look at this example, which I didn't get to, if you look at malloc, what I forgot on this slide is that this malloc impulse should be called in the open, but actually there are parts that are really critical that do run in the open. So the way malloc is implemented is we malloc in the open, and then if you abort that transaction, we free it for you.
Sounds good, thanks.
Do you have idea what the overhead of your STM is on the C++ code?
Yeah, like 3 to 3.5x.
Are there optimizations in STMs that you think that you'd be able to apply here? Like, for example, like you don't have to write to the write log for new objects and things like that?
Yeah, so we do have some of those optimizations. So if you're newly allocated memory, we have like I think it's a red-black tree where we track that. And we skip, so testing for that is more performant than performing the write to the write log. So we do that. For the VM's transaction log, I've played with an idea for epochs, so tagging every allocation with an epoch. And if you write to and epochs are monotonically increasing, and every new transaction bumps the epoch count. And every allocation can grab its epoch from the epoch count. And then you can elide writes to the transaction log if you write in an epoch that's less than or equal to your allocated epoch. That was inconclusive if it made anything faster. I think that might end up being profitable, but there are probably other ideas we haven't explored also.
How does distributed STM work?
Right, so the whole metaverse programming vision that Tim has, we're working on something called distributed software transactional memory. It's not, the goal of that is not yet to be persistent, but it is to write code that largely looks single-threaded, but is distributed across multiple machines. And AutoRTFM is a foundational technology for that. So what you have in our model is objects that can be owned by servers. And if your C++ code tries to access an object not owned by your server, you actually abort the transaction, request that object be migrated to your server, and run the transaction again. So like this technology we've built has actually been really useful in other projects we're working on.
So I have a question about the application of this logical part. Looks very interesting from the programming language design, but I wonder how it is useful for game development. Like why, why do you need all that unification magic for scripting games?
Yeah.
Ideally, if you have some example, that would be awesome.
I don't know if I have a great example for that. I think there are aspects of the logic stuff that's used. I mean, to me, I find more of the functional subset more useful than the logic subset, especially because there isn't, like in Prolog where you have the search space semantics built into the language, that's not built into verse, which to me I view a little bit more interestingly. But I think, I don't know, I don't have a good answer for you on why do game programmers need logic programming.
Because Tim said so.
Well, that's why we're implementing it, but that's not I'm not going to convince you with that. No, I don't think so, yeah.
So I have kind of a related question. For the shipverse, so you already have a few of the esoteric features, I would say. Did you like study how developers use them? Do you have like...
Yeah.
Because they have access to the code, so do they actually use this kind of... this kind of features?
So shipverse doesn't have leniency, doesn't really have unification variables.
Okay.
In an interesting way, does have software transactional memory.
Okay.
Does have coroutines. The most interesting part of the language I've seen used widely is coroutines. Like I talk pretty regularly with verse developers, and it's really interesting to speak with them because they kind of don't care about the language. What they care about is making really fun games. Coroutines are the most like extensively used feature of the language. Like I didn't talk about it at all, but there's a lot of constructs we have for writing cooperative multitasking code using coroutines really easy. And that's like the thing I see developers using the best. I don't see them using software transactional memory in interesting ways. But yeah, coroutines are probably the one they use most interestingly.
All right, well, thanks a lot, Sam. And let's thank the speaker.